this is typically what my desk looks like when I start a new project. And then maybe something more like this. And this being the last talk, I should really have changed this to like a wine or a beer stain, but then this happens, right? I'm Joël Kuiper, and I work for a company called Dr. Evidence, which is a consultancy and software firm in the United States. Which is why I do this through a remote company that I founded myself called Vortex Systems. This talk is growing a biomedical search engine in Clojure. And this is really the culmination of 3 years of work that we've been doing in this space. And I thought it would be nice to show it off a little bit. But given that it's the last talk, we'll keep it short. So there's just 3 parts in this, like setting the stage, growing the project, and then some lessons learned. We can all go for a beer. So the stage. We're in a field called evidence-based medicine. And evidence-based medicine is the approach to making medical practice better. And the way to do that is by optimizing the decision-making, by making use of the good evidence and well-conducted research. So this is a little bit vague. You can sort of gouge at the idea that in medicine, especially if you treat people, you want to make use of the best possible evidence available. So anecdotal evidence or something like that doesn't really fly. So they came up with this nice pyramid, right? So this is what they call the evidence-based medicine levels of evidence pyramid. And at the bottom, you have animal studies and laboratory studies. And those provide some guidance on maybe drugs or treatments, but they're not super useful in the real world. So you go up to case reports of people actually having a disease. And if you go all the way up the top, you have like the pinnacle of evidence, which starts with randomized controlled trials, where you give a population a certain drug and another part of the population a different kind of drug, and you control them, and you try to control the environment as much as possible. So you're actively monitoring the effects of the substance you're using or the treatment you're giving, and not so much random noise in the population. But there are a lot of these things conducted, so you have to do things like systematic reviews and meta-analysis, and that's what I sort of want to get at. So this is what a typical randomized controlled trial looks like. This is not a joke, this is just a PDF in a medical journal. This is how these things get published. They're usually like 5 or 6 pages long, and they're written usually in the form of some drug versus some other drug in some condition. And that's fine. But there are a lot of these things being published. This is 3 of them, but in fact, about 100 of these are published every day in 2015. And over 1 million medical articles are published each year. And this is on an exponential growth curve. So this problem is going to get worse and worse. So what they do to see if the evidence that's being collected in these randomized controlled trials are actually worth their salt is they do a trick called evidence synthesis. So they take a bunch of these PDFs, they read them, they extract data, and then they write either a systematic review or do some statistical analyses on the results of these randomized controlled trials to give a better idea. So that's the space we're in sort of doing systematic reviews of all the available evidence, the best possible available evidence, to provide guidance on treatments, and maybe along the way discover some new interesting properties. So the way these systematic reviews are typically being done is through this slide, and I won't bother you with the details because it's both horrifying and hard to read. But basically, on the top, people do a search in literature databases. These are things like PubMed or sometimes just straight up Google, and they return somewhere in the orders of tens of thousands of these documents. And then they go into screening, right? So they decide whether or not some of these are either duplicates or if they're even relevant or not. And then they assess them for eligibility. So typically, these are done in the context of what's called a framed question. So you want to know the influence of some drug in some population, and then particular for some outcomes. And at the end of the slide, you'll see like it's 46 studies that are left after this tedious process. And then the money shot in those publications is usually a chart like this, where they compare the efficacy between things. So really the process is search the known literature, screen the literature for relevancy, extract the data from the PDFs. This is a manual affair. People read this, read the PDFs, put them in an Excel sheet. And doing some very advanced statistics on top of those. Report the findings, again in a PDF, and then someone at some point has to repeat this entire process. This takes years. This is no joke. This is a very, very slow-moving field. And you have to wonder whether or not this problem should even exist, right? Why are these things being published in PDFs? Isn't there like a standardized data format for this? But there isn't, and that's part of the reason why we're here. So the question is, that was asked to me about 3 years ago, is can we do better with AI? And I said, maybe, and I quit my PhD over it because they offered me a bunch of money. I said, sure, I can give it a stab. Under one fine condition, I get to choose the technology stack, and I chose Clojure, because if anything, I wanted to do this in Clojure, and I'll go into a little bit of details why. But it turns out to be really hard, mostly because of this nice XKCD slide. So it's like this field, our field has been struggling with for years, and I come in, it's like, sure, I can solve this with algorithms, and I give it a stab for like a couple of years, and it turns out, shit, it's really hard. And one of the reasons it's hard is because it always exists at an intersection of things that you might not be aware of as a developer. So it exists at the intersection of technology, people, and processes. Like the naive me at that point said, like, why isn't there a structured data format for this in a database somewhere that I can just query and pull and do the statistic on it? And it turns out there isn't, and there are good reasons for them, and there are sort of bad reasons for them, but that's the culture and the process that you're in, and you have to be aware of those. So the first step when you tackle any problem is to learn the domain. And when you start learning the domain, you have to be extremely respectful, because these people have been doing this for decades, right? You can't just go waltz in and like, I'm gonna solve these algorithms, and then expect it to work. For one, they won't probably listen to you. And the other is that there are intricacies in this field that you have to be aware of. So at some point, you have to learn the domain and be comfortable going to not just a Clojure conference and talk to these people, but actually go to the domain field and talk to these people and have a beer with them as well, and then sort of get this idea in your head of how it fits together and reflect on that. But once you know the domain a little bit, and I was lucky, I had a bit of experience, not that much, but I had some experience. You get to think about things. So you start to grow your product, start to grow your idea, and there is this very nice quote that I'd love to share. This is from a blog post I read through Hacker News, so I'm not sure about the authenticity. I'm just going to read it. Like, if you start to grow a project, it's like trying to build a 10-piece puzzle, except you have to find 10 pieces within a pile of 10 billion pieces, all of which are square, and you don't know what it's supposed to look like at the end. Good luck. And that's really how I felt at that point, right? Because I didn't know how to solve this problem, and I had like all the tools available in the world, and I made choices to do Clojure, so that was constrained. But then, of course, what's next? What is it even supposed to look like? What is it even supposed to do? And learning the domain there helps. So this was the initial idea. So we wanted to annotate public knowledge, or public medical literature, with medical ontologies or knowledge graphs. And this is not a super novel idea. It's like back in the 2000s, people were doing this, but we wanted to do it again and better, and do it on massive sets of public knowledge, and somehow harmonize all these different areas that people are currently querying the data for. And then being able to interactively expand or contract and update these search parameters as they go along, as they do their project, so they don't have to go back each time and go to the 15,000 things and then screen them back. So we really wanted to make this interactive, and then provide some high-level analytics on top of that to just give a bird's eye view. So that was sort of the initial idea. So this is what we do. We annotate natural language from medical documents. This is just an example from one of those papers I just showed you. And the process is fairly straightforward natural language processing, where we do first part speech tagging and dependency parsing, Then we deal with synonyms, acronyms, abbreviations, misspellings, all that good stuff, which gets fairly complicated as you get into the details of it. And we link all these things that we find in the medical documents with concept URIs in RDF. And RDF is this ancient technology from like the 2000s, right? Nobody does this anymore, except we do, and it's awesome. So we wanted to be able to reason about very large collections of conceptual indices, and RDF turns out to have very nice properties for doing that. It's able to scale massively in any direction, and it provides a Prolog-like query system, so you're able to do that. And then what we wanted to do is also annotate the different types of things that you find in the natural language with the framed questions that I previously mentioned. So we wanted to know in this text, what is the population of interest, what is the outcome of interest, and what is the interventions that were used in this specific text. We use a bi-LSTM CRF neural network for that, which officially puts us in the type of companies that actually use AI. There's recently a nice Forbes article that 40% of the European AI startups don't actually use AI. Well, for one, we're not a European company strictly. Next, we're not typically a startup, but we do use AI, so we felt really good about ourselves. And then a huge part of screening is to filter out the noise documents, like the case-controlled studies and the animal studies and all that stuff. So we really wanted to do very reliable document class prediction. So is it really a randomized controlled trial? What does that give us? Well, that gives us, for each of the terms that we find in the text, we get this conceptual graph attached to them. And that is very useful if you want to do things like search. For example, this particular drug in this sentence is known to be an immunomodulator, and it's known to be a selective immunosuppressant, and even a monoclonal antibody. So instead of specifying exactly the list of drugs, the user would now be able to go in and says, like, I want to know all the monoclonal antibodies that are related to this particular characteristic. And that turns out, and while doing that, deal with all the synonyms that are attached to it and all the drug codes and all the other points, and be fast about that. Similar for the multiple sclerosis example. So you're able to iteratively look at these subsections of the knowledge graph. So we applied this trick across literature. We currently have 31 million items, which are things like clinical trial reports, publications, meeting abstracts, all those kind of things, across 1.3 million of these concepts, which are uniquely identifiable medical things, which encompass about 2.8 million terms. So those are the actual labels that are attached to it, which works. It's nice. So we were happy about it. Clojure helped us there. This is sort of what the search interface looks like at that point. So you can say, like, descendants of multiple sclerosis in title. I want it to be predicted to randomized controlled trial or like a PubMed review. And it gives you overviews of co-occurrences, like these are the top interventions found in this document set, or these were the top outcomes found in this set, or any cross-section. Typically, sort of the user interface looks more like this. We have a couple of modules. Standard bootstrap, but it works. And then if you go into the details of a document, you can also see the retrieved metadata for those and look at the links between the documents. For example, the clinical studies often have mentions to other articles, and being able to plot those on a timeline gives you a nice view of the available evidence originating from a certain point. Our stack to build this is bog standard to some degree. So we have, on the front end, we have Clojure script. Reframing reagent, we still use less CSS because we inherited that from a previous project. Boot builds, so very excited about the new boot changes coming up. Also a little bit worried, but we'll see, we'll get there. Our backend is Clojure on the JVM, Postgres, Elasticsearch. The one nice trick is that we use a plugin for both Postgres and Elasticsearch called ZomboDB, which keeps them nicely in sync. And these all communicate with each other through RabbitMQ. And when we started that project, unfortunately, the data science story in Clojure wasn't that great. It's improving, but so there is still some incidental Python thrown in the mix, which also communicates over Hermeneutic. So yeah, at that point, proven technology. We have active users that are excited about it. That's good. From the blank cup of coffee and an empty slide, we managed to build a product people are excited about. I mean, that's still something good. But we also had still very major academic and technological challenges at hand. One of the main ones that is still unsolved in natural language processing at large is the issue of word sense disambiguation. So if a user types in stroke, there is a realistic chance that it will return documents about golfing because of the backstrom. And those problems are more prevalent than you might imagine. For example, a major heart attack could also be a major in the army that's having a heart attack, right? So that's a tricky problem, and it requires a deeper level of natural language where you can't match these things. And there are solutions to this, but they also are very computationally intensive. And we have a constraint that it has to run on half a rack of Supermicro running at the campus. So we're not using any cloud. I physically moved the machines there. It's not a hard constraint, but we'd like to keep it like that for as long as I think it's possible. Because constraints are good, right? If it has to run in half a rack of Supermicro, then yeah, you're speedy and you're not blowing up an AWS bill. Because if you hook up some of these things that might have exponential growth characteristics to your Elastic thing, you run out of money faster than you can say cloud. And these things are CPU bound in a lot of cases, so yeah. But then, because people were excited, the feature requests came in, right? And this is the point in any project where you're sort of like, all right, we have something nice, it works. So there are academic challenges that I want to solve. There are things that I want to work on to make this better, and that I think are still somewhat unsolved. But you have a growing list of feature requests from users. For example, can we do something like influential authors or key opinion leaders? Like, okay, sure we can. And we built this widget. But then a whole lot of problems fall out of that, right? So problems with names is that you have name synonymity and name homogeneity. And roughly that means if it's the same name, does it really mean the same person? Or if it's a different name, does it mean like the same person? And this happens a lot. And what even does influence mean, right? So we settled on doing PageRank on the co-author graph, but it's an open question. How do you even draw these sensible networks across the thing? There are all these open questions. So we use Dijkstra's and spanning trees, and nobody ever reports their affiliations consistently, so you have to build like several levels of fuzzy matching in there, and et cetera, et cetera. And then Hofstadter's law kicks in, right? It always takes longer than you expect, even when you take into account Hofstadter's law. And this is a known truth. It's recursive. We're Lispers, so we like this. Or things like a competitor that has X, can we also do X? Well, yeah, maybe you have to think about it. Mind goes racing. And, can we also use the blockchain? Right? And I would attest that this is a trap. Don't give in to this. The majority of projects that I've been part of either struggle or fail at this point, where you build some project and you open up the floodgates and people will request features, and now you have to think about where to put that stuff and if it even works with your initial vision of the product. So what is growth in this case? Well, I can look at the dictionary definition like a proper Clojurian, but I'm going to skip that. I have a visual metaphor. This is the growth of crystals in a petri dish. I think they're tin crystals. And I think this is a very apt metaphor for a lot of what software development is. It crystallizes out. So you start with this one thing, and it then starts to grow into these more or less brittle things. And like crystals, projects solidify and become brittle when growing. There's this other concept from metallurgy called work hardening. So if you work a piece of copper hard enough, it becomes brittle and falls apart. And I think this is typically how a lot of projects are being developed. And it might not be the right way of doing it. So maybe growth here is the wrong concept. And I had a very silly example from psycholinguistics. So there's this phenomenon called Booba and Kiki. Which one is the Kiki one? Show of hands. Is the left one or the right one? Left one? Right, so this is universal. This is a universal thing. The left one is the Kiki one, and the right one is the Booby one. So I think we should think about projects more in terms of whether or not they are these brittle, crystalline shaped things that sort of grow in arbitrary directions, or whether or not they have the smooth edges where you can still mold and shape them. And I think Clojure, in this case, is a really good choice for these types of projects, where you are uncertain from the get-go what you need to build. You build something, and then you have to change it. Because it helps you shape projects and not grow them as crystalline structures. Why? Well, I guess I can just very quickly go over this. It's a dynamic language with immutable data structures, which I think is the best of both worlds. One, you don't have to worry about types, so that means less typing, less worrying about those things. You can move stuff around easily. It's not type safe, but then again, don't make a lot of type errors. Typo errors you'll always have. But the immutability gives you a really nice guarantee of not having to worry about state all that much. So there's less chances of errors. I think in total, after the past 3 years that we've been doing this, we maybe had 1 or 2 type errors in production that we had to fix at runtime. Just don't bother. REPL-different development, you can play with these things. It has been proven, especially on the front end, where you have things like hot code reloading, extremely valuable. It has a sensible dependency system. I cannot tell you how many times I've almost gave up getting my Python machine learning stack to run again after a dependency update, or even a transitive dependency update that somehow at a point release broke the entire build, or even broke the entire machine learning system. This doesn't happen in Clojure for some reason. We have a sensible dependency system, and partially because it's relatively slow moving. And I think that's a huge advantage. Compared to, say, Python or Node.js or any of the other languages, and I'm not picking on any one in particular, having a slow-moving language means that you have a solid basis about reasoning about your actual problems, and not so much whether or not you should update your Angular version. Because that's the Frankenstein monster, right? We know this. And it draws from decades of Java and JVM and Lisp history. So a lot of these things we just include, and they work. Or we grab them from a paper from the 40s. And, well, 40s is a little bit exaggerated, but a 40-year-old paper, and it still works, mostly. And it has a very good story for getting rid of things, because things are just arguments to other things, and they're immutable. You can just cut them out if you want. And code is very heavy. You want to have the least amount of possible code in your code base ever. So don't drag it along. And this really means that for me, if I work with Clojure, it feels more like Play-Doh rather than like this crystal structure. And I know that's a little bit of like a fuzzy-wuzzy soft definition. Then again, it's almost like 6 o'clock, so I think that's fine. When you think about a project, try to imagine in your head what it feels like to change it, right? Do you feel like these spikes in your hand, or is it actually pliable? And Clojure projects, in my mind, are extremely pliable. You can move stuff around, nothing breaks. It's not brittle. And that's a very nice property that we have used successfully. And so, lessons learned and how to deal with this. Well, Clojure is a good thing. Well, first of all, in the next life, I'll probably become a civil engineer to work on something more concrete. That's the job. Don't bother with priorities, milestones, planning poker, timekeeping, productivity metrics, etc. If you're not clear on what you need to do, this won't help you. This won't increase your productivity at all. In fact, it will hamper you. So try to push back on these things, and if you're in a position of management power, try not to implement these things. Because I've noticed developers sometimes actively want to have these things, but it's really bad for them. It's really bad for us to have these things. So don't bother for as long as humanly possible. Accept that your backlog is infinite, right? This is not something that people would like to hear at some point, but you have all these sprint sessions and you do backlog pruning and you have people coming in and you need to prune it. No, the list is infinite and it will grow forever, and it only matters which thing is on top. Take breaks. It's very important. And the only thing to manage here is to have this vision and have it coherent and make your software pliable. Very concrete things, what we learned. So this is my sort of opinionated section. This doesn't apply to any project. This applies to the types of projects where you're not typically sure what you're working on. So there are a lot of cases where you're working on like hard algorithms work, or you're doing something for the umpteenth time, to use a hickey-ism, then this doesn't apply. But if you don't know what you're working on, logging and metrics for UI UX decisions, just don't bother. They will only tell you the things that you already know somehow, and no amount of feature tickets based off those will save you from a really bad idea. And you'll have to maintain it, right? And code is heavy, so now you have this entire stack of things where you have to measure and do A/B testing. And if anything learned from the recent problems in psychology is that most of these things are not reproducible anyway. Unit tests, we don't typically bother with a lot of unit tests. In a fail-fast system, which most systems should be, in my opinion, the end-to-end test succession, you should just crash. It's probably the only sane thing to do. Super complex cloud deployments. Contested thing, I know AWS is extremely popular. We made the choice that bare metal and bash will do. And one thing that's also a little bit contested is specs. We do have some specs at the API boundaries, and we do check them during development. But in a lot of cases, they tend to crystallize out your application in directions that you're not typically comfortable with, and it makes them harder to change, because now you have to change two things instead of one thing. So a very concrete example is that we have like this widget thing in our system, and it has to display like a title, right? So what is a title? It's like a string. All right, so insert for the widget spec is a string. But now we want to display an icon there, and it's just React, so we can just pass in any arbitrary object. But now you have to change your specs to make sure that it also accepts like a vector of things. Whereas if you didn't, you wouldn't even have the problem. And this creeps up in a lot of cases where you have to, you know that it's going to work because you tried it on the REPL, and then you run it and it's like, oh, the spec is failed, and now I have to update the thing. It doesn't typically work, for me at least. Do spend time on creating a mental picture, a story or a vision, and communicating and listening to everyone involved. This is something that I had to learn more, and I think a lot of people could benefit from learning from that. And then learning the domain more broadly and deeply. And while you do that, try to develop a feel for quality. And that's a super hard thing to explain what quality even is, or how to define it. And the best way I found to sort of explain this is going to Solutive Philosophy of Zen and the Art of Motorcycle Maintenance, where Persix talks about what is quality. And he goes into the idea that it's sort of this pre-intellectual notion. You know this up front. You start to rationalize it at some point, but when you look at the product, you sort of already know. And you have to develop that feel somehow. Also, I need my sleep. I need about 8 hours a day and about 10 at night. This is my other hero, Bill Hicks, unfortunately late. Yeah, this is really important, and not having the timekeeping and the priorities and the milestones and the quarterly updates attached to all of your tickets in Jira really does help with that. Because sometimes you just don't know. You don't know what you have to work on. But then when the feature requests come in, learn how to say no, respectively. I think as developers, we're probably in an extremely privileged position where we get to understand parts of domains that we otherwise probably wouldn't have gone into. And at the same time, we have the ability to actually build it, right? This position comes with great power, but also with great responsibility. Learn how to say no. Like if someone comes up with a silly idea, like let's do blockchain, don't go running around saying like, yeah, we should do blockchain, it's awesome. Like, no. But conversely, learn how to say yes, because in the unfortunate truth is that we are extremely limited creatures, especially when it comes down to reasoning about complex abstract systems, and especially complex abstract systems where not everything's known up front. Which means that you'll be wrong a lot. And one of the most humbling experiences I've learned in life is learning how to program, because that will teach you how wrong you are most of the time. So yeah, in life you'll be wrong more often than right if you go about sitting behind a computer at least. And that means that people will come up with good ideas, and people will come up with changes to your system that might not even be comfortable for you. But sometimes you have to say, yes, you were right. This is a bad idea. We should do this again. Or, yes, this is a super good idea. We should spend 3 months doing it. But while doing that, have to remember that software is also a social construct. It exists in this space between technology and where you're actually trying to deploy it and the environment you're trying to do. So in our case, this is evidence-based medicine, where people take years reading PDF files and then doing statistical analysis to then publish them again in PDF files. This is the thing we're in. But it does give a strange juxtaposition, because the people doing the systematic reviews themselves have gotten a little bit worried about this idea, because you'd expect the people who do these systematic reviews to be the extreme experts in their domain once they're done. But this is not necessarily always the case. I mean, they read all the documents, and they go about all the screening, and they do all the extraction work, and they do all the analyses. I mean, they should be like the expert in the domain they did the systematic reviewing. But it's such a mechanical process that it lacks any form of insight and reflection. So they've been moving towards a different type of system. I'm not sure what the S is doing there. But this is sort of what they call the hermeneutic review cycle. It's a biblical term where really the search and acquisition is just part of the larger cycle of analysis and interpretation. And this goes on and on forever, and at some point you have to just call it quits. So the end result here is not that PDF document that's published that says this drug is better in this drug in this population under these circumstances, but really the expansion of your horizon and understanding about the domain. And when you put that central, suddenly you have like this nice juxtaposition, right? How do you develop software, and how do you develop systematic reviews? And this is sort of where we want to go next. So we have built a tool where people are able to search their literature really efficiently and be able to export them. And there are other tools at our company that are really effective in doing all the statistical analyses and doing the extraction from the PDFs. But it's a mechanical task, and at some point, the insight has to come back. So very abstract again. Well, we're going back to the drawing board in some phases to see how we can help people gain understanding while they're interacting with this literature, and not just look at 50,000 PDFs. That being said, Clojure is awesome. I made a boring slide, so I gave myself like one little indulgence, and then I might like make this up like a flame. That's it.
Thank you. So I think finally we heard blockchain that makes this conference successful and trending. So any questions? Okay.
Really interesting tool, thank you very much. I was wondering, are there any plans of taking the product one step further up the hierarchy in the pyramid and actually performing the meta-analysis itself? It would involve things like extracting values from tables and from the text and things like that. But I think there are the tools available to do that type of task.
Yeah, so that's one of the things our company does as a service, but it's still a manual affair. So they get the documents and they'll extract it and they'll run the statistical analyses in like the whole pipeline. Automating that is definitely something we're super interested in because that would save everyone so much time. And especially if you do this automated, you already have this database, so people only have to do it once instead of every time. Thing is that with the current understanding of how to extract table data from PDFs in a natural language consistent way gets you maybe 60–70% of the way there, and then someone still has to come in and can check it and fix it. And that's the unfortunate truth of when you're doing machine learning type stuff in production. Like an F-web measure of like 8 or even 9 is awesome, right? You can publish papers off F1 measures of 8 or 9. But the 10% is where the trick is at. And that is really the decision whether or not someone has to come in and check it again, or if you can let it do its own thing.
Next question. I saw a couple of hands. Yeah, there and there and there.
Hi. A stupid question about the tech stack, but you mentioned you were using RDF and Sparkle, but you didn't really have a triple store in your tech stack. So are you guys running that off of Postgres, or did you roll your own thing? I don't know.
No, I omitted that. For now, we're using Jaina and Fuseki, the Apache projects. We may consider Allegro Graph at some point, which is developed by France Software, but Jaina and Fuseki is the release.
Cool, thanks.
Yeah, on that note, you should keep an eye out for the Crux database that's coming out. That actually has pretty nice support for RDF stuff. But I wanted to ask you, and which is fully written in Clojure and everything. Yeah, it's super interesting presentation, and it's baffling that like this is the state of the world, that like all this information is captured in PDFs.
Yeah.
Is there anything moving in this space? Anyone trying to get people to publish actual readable formats?
Yeah, so there are, but there are, so again, social contract. There are several problems with that. One is some publishers have tried this. Elsevier, for example, is active in this. But then none of the other publishers do it, so you still run into the same problem. For clinical trials themselves, the FDA and I think even the European Medicine Agency have started mandating that people publish their results in sort of this unwieldy XML format, which is parsable, and if you forgive its warts, it works. But the problem is that a lot of these things span 50 years, and no one is going to do it retroactively.
Any more questions?
So you talk about learning how to say no and learning how to say yes. So I think that's a very interesting insight. Can you elaborate a little bit more on when you have a feature request? What is the decision process for you to leading to yes or no?
That's a very good question, and I think that might be a talk in itself. But the one key thing is, I would say, to have knowledge of the domain and then work with the people who are trying to solve an actual problem. So watch them as they go. and then it might sound silly, try to make a decision for them sometimes, because a lot of users don't know what they want. And sometimes, and especially when you consider software, for a lot of people this is black magic, right? So they might not be aware of what's possible, or what's easy, or what's hard. So I would say try to learn the domain, interact with people, and while doing that, sort of develop a feel for quality. Like, what are the things that they're really liking, and what are the things that they're not really liking. You have to sort of emphasize to some degree.
There is one.
I was just wondering if you did a lot of performance optimization with those numbers and this rack, or did it all work out of the box?
So yes, we do quite a bit of performance optimization, not as much as we'd like. One of the major bottlenecks right now is that if we make a major change to the way we parse natural language or do machine learning predictions, we have to do it again. We store the results, right? This now takes about a week and a half. And that's, I mean, it's a nice thing to say, like, we're going to do the reindex and then wait a week and a half, but ideally you do this overnight, so there's room for improvement.
Where did you get your original data set from? And does your system work, or can it be adapted to other data sets?
Yeah, so there are two parts. Like, one is the domain-specific knowledge and the ontologies, and one is the actual literature. The domain-specific ontologies, for a large part, come from a project by the National Library of Medicine called the Unified Medical Language System. They publish a lot, and if you coerce it in the original meaning of the word into RDF, that works. And then there are other public data sets like the human phenotype ontology and the gene ontology that you can interact with. And then there's proprietary data that the company itself has built over the years. For the original documents, we started off with PubMed, which you can just download as zip files, clinicaltrials.gov, RSS feeds. This is a growing list of things. So we're also actively pursuing contracts with the actual societies like the American Heart Association and American Society for Hematology, those kind of things, for them to give us the data.
Any other questions?
How big is your development team, or is it you alone?
No, it's 5 of us, 2 of which are in the audience right now. And I forget to mention, we're entirely remote, so we did this from home.
So, I think that's a wrap. Thanks a lot, Joel, and